Okay, so we're going to carry on with the number systems. You should have watched or gone through the other video, which was the introduction to this. One of the things there wasn't too clear when I listened back to it was about the high voltage and low voltage. Just need to make sure that's the actual particular circuits that are right down into the computers. They boil down to just a whole series of circuits which are either high voltage or low voltage, and depending on if they're high or low voltage and how they put them all together, that'll make up all the ones and zeros for a binary system. And that's why binary is used on a computer, because it literally boils down to high voltage or low voltage. Hopefully get that across this time. So that's what we did last lesson. We had talked about a bit about bits. We talked about analog versus digital, analog being continuous, digital being something that only computers really can use because they can't handle analog. They have to keep taking readings over and over again to try and get it as accurate as that we can hear naturally as analog listeners, or analog processors I should say. And we also then went over the different bases: decimal or denary, which is base 10, which is based on our human counting system of our 10 fingers; binary, which it talks about, which is base 2, made up of digits 0 and 1; and hexadecimal, which is base 16, which is made up of the digits 0 to 9 and the letters A to F. But anyway, let's carry on. Let's get on with really a bit more mathy type stuff. So let's do that. Maths refresher. So to the power of the exponent, x to the power of y is written as x to the power of y, with y as what's known as a superscript. Now, x to the power of 0 is always 1. Now, x could be your number system. So, for example, if it's base 10 denary, 10 to the power of 0 is 1. If it's binary, which is base 2, 2 to the power of 0 is 1. Or base 16 hexadecimal, 16 to the power of 0 is, 1. That always forms the first column when you're dealing with your number systems. That's why all number systems, the first column is 1s. Now, the next column normally is the next one across, which is to the power of 1. So anything to the power of 1 is itself. 10 to the power of 1, 10. 2, base 2, binary, to the power of 1, 2. I know I'm labelling the point here. Base 16 to the power of 1, 16. So 0, 1, if you know your patterns, the next one's going to be x to the power of 2, or x squared. And that's normally the third column. If we go from the columns really from the right hand side. And these are that number multiplied by itself. So a base 10 system, we know the first column are the 1s, the next column are the 10s, and we know the next columns are the hundreds because it's 10 to the power of 2, which is 10 times 10. And for binaries, it'd be 2 times 2, which is 4, or 16 times 16, which is 256s for hexadecimal. Next one, x to the power of 3 is the same as x multiplied by x multiplied by x. So again, we know that the next column in denary numbers in decimal is the thousands, 10 times 10 times 10. In binary, it's 2 to the power of 3, 2 times 2 times 2, which is 8. And then for hexadecimal, 16 times 16 times 16, which is 4096. Therefore, x to the power of n is x multiplied by itself n times. 10 to the power of 4 would be 10 times 10 times 10 times 10. Or 10 to the power of 5 would be 10 times 10 times 10 times 10 times 10. 2 to the power of 5 is 2 times 2 times 2 times 2 times 2, and 16 to the power of 6 is, you get it. Right. How you're used to representing numbers. First of all, it's denary, powers of 10. You group the digits into columns. That's base 10. In computer science, as you know, we call it denary, but sometimes it's also referred to as decimal. So take the number 327. That is 3 100s, 2 10s, 7 1s. Add those all together, 300 plus 20 plus 7 gives you 327. Or we're just used to calling it 327. Now if you put that into columns, first column is your 10 to the power of zeros, that's your 1s. Then your next column is 10 to the power of 1s. I'll get my mouse pointer out here. 10 to the power of zeros is 1. 10 to the power of 1 is the 10s. And 10 to the power of 2 is the 10 times 10, that's the hundreds. So, 3 100s, 2 10s, 7 1s. So really, if we started calling it, rather than 327, if we said, oh, it's base 10, 327, then we'd know that, oh, it's 3 of the first column, 3 of the third column, 2 of the second column, and 7 of the first. Or really how we normally work is the other way around. We actually go from the right to the left, and we'll say, all right, there's 7 1s in the first column, 2 in the second column, the 2 10s, and 3 in the third column. So look at these kind of things. The rightmost column, as we know, always starts off 10 to the power of 0, so they're always the 1s. And the next one's the 10s, 10 to the 1s, then 10 to the 2s, 10 to the 3s. So 10 times 10 times 10, 1,000, 10 times 10, 100, 10 times 1, 10. So 327, as we talked about, and then look about 5. Well, 5 is 5 1s. 5 times 1, 5 times 1. Nothing, 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 because there's nothing left. There's no 10s, there's no 100s, there's no 1000s, there's just 5 1s. What about 5,326? Or thinking about it is 5326. It's made up of 6 1s, 2 10s, 3 100s, 5 1000s. Then add them all up together. 5 times 1,000 plus 3 times 100 plus 2 times 10 plus 6 times 1 would get you 5,326. Now look, in base 10, even though it's a base 10 system, you don't have a 10. You only go up to 9, which is why in binary, when you have a base 2 system, you don't have 2s in it. You only go up to 1. If you have a base 16 system, you only go up to 15. And we'll go more about that in another lesson about why we don't actually use 15. Because single digits are only allowed in each column. Otherwise it gets confusing. So think about it this way. If you were using a base 49 system, what would be the number you'd go up to? You'd go from 0 to, not 49, it'd go up to 48. Let's look at binary. We know it's base 2. We know it consists of 0s and 1s. Think along the same lines as denary. Split it into number columns. Remember, the right-hand most lane was 10 to the power of 0, and then it was 10 to the power of 1, then 10 to the power of 2. Well, substitute the 10 for the base 2, whatever base system you're in. It'll be 2 to the power of 0, 2 to the power of 1, and the next column will be 2 to the power of 2. Look a bit like that. 2 to the power of 0 is 1, 2 to the power of 1 is 2, 2 to the power of 2 is 2 times 2, 2 to the power of 3 is 2 times 2 times 8. So these are the 1s, these are the 2s, these are the 4s, and these are the 8s. So look at this binary number. It's got no 1s. It's got 1, 2. It's got no 4s. And it's got no 8s. So what do you think it is? No 8s, no 4s, 1, 2, no 1s. So it's 0 plus 0 because it's no 8s plus no 4s plus 1, 2. So we've got a 2 plus no 1. So add it all up together. You get 2. So 1 0 in binary is 2 in denary. So that hilarious key question we had at the beginning, there are 10 types of people in the world, those who understand binary and those who don't, because it really should be read as there are 1 0 types of people in this world, those who understand binary and those who don't, because we know that 1 0 in binary is 2. So in other words, there are 2 types of people in this world, those who understand binary and those who don't. Funny stuff. I need to get out more. Anyway, what would 1 0 0 in binary? And get out of the habit of saying 100 because you're going to get yourself confused. Call it 1 0 0. So what's that look like? Well, let's put it into the columns. Right. So the right-handmost one goes in the right-handmost column, 0. Then the next one, the next 0, goes into the next column, and then the next one, 1, goes into there. Now there are no other zeros to the left of that one in the 1 0 0, so you can fill those all with zeros, but we're using 4 columns at the moment, so that's fine. So just fill up with a 0. So we've got 0 1 0 0. What's that going to look like? Well, that's no 1s, no 2s, 1 4, and no 8s. So what do you think that is? It's 4. So to convert a binary number to denary, first of all, put each digit into a column. Then once you know they're in the right columns, you'll know what the denary or decimal equivalents of each of those columns are. Is it how many 1s are there, how many 2s are there, how many 4s are there? Every time there's a 1, you want that value. So if there's 1 1, you're going to add 1. If you find 1 4, you can add the 4 to it as well. So let's look at this. Converting the binary number 1110 to denary. First of all, put them in each column. There you go. Now, work out the denary values of each of the columns. So the right-handmost one is the 1, then ones, then it's the 2s, then it's the 4s, and then it's the 8s. And then anywhere you see a 1, you're going to write that down. So look, there's 1 8, there's 1 4, there's 1 2, and there's no 1s. So it's going to be an 8 and a 4 and a 2. Add those up. What do you get? 8 plus 4 plus 2 is 14. So you now know that 111 in binary, in base 2, is 14 in denary or decimal, base 10. Now, we represent these different bases. It can get confusing. If you see 100, is that 100? Is that 100 in binary? Is it hexadecimal? So what they do is they use a subscript and the number underneath it in computer science to tell you what number base it is. So look at this. 10101001. Little 2 there is telling you it's binary, it's base 2. Next one, base 16, 97. So 97 is not 97, it's 97 in base 16. More on that in another lesson, don't worry about it. 389, it's base 10. Okay, it's denary, so that would just be 389. Most of the time in maths, you're never going to write that down because it's always base 10 you're using. But in computer science, we've got to be a bit more careful. That's why you'll see it occasionally down like that. Look, have a go. How are you going to do these? All right? Just before you pause the video, think about how you do that. You're going to put each of those digits into a column, then work out the denary values for each of those columns, and then every time you see a 1, you just add that denary together. So pause it, write them down, and I'll come back in a sec. Pause it. Right, here you go. So, think about that. There were 0 1s, 0 2s, 0 4s, and 1 8. That's 8. Next one. There was 1 1. There we go. There was 1 2. There we go. There were no 4s, and there was 1 8. Add those together, you get 11. And the last one there. That's one of everything. So there was a 1 1, there was 1 2, there was 1 4, there was 1 8. Add them all up, you get 15. Now, at GCSE, you work in bytes. So they'll ask you normally to write your binary numbers in 8 bits. Be very careful. That's how they try and catch you out with the questions. They'll give you something, and they'll just write in the question somewhere, give your answer as a byte. And they expect you to use 8 bits. Now, the bits, remember, are the 1s and 0s. So you've got to use your number as 8 digits. So even if it's 1, you'll have to write 7 zeros and then the 1. Remember how you do this? So I've only shown you the first 4 columns, but you know it's 2 to the power of 0, 2 to the power of 1, 2 to the power of 2, 2 to the power of 3. Well, the simplest way is just double as you go along. You know the first column's 1, so just double. Double that, it's 2. Double 2, 4, 8, 16, 32, 64, 128, boom, that's it, done. When you go to mess around with binary, make sure you know those. Common mistakes is people start at 2. Or for some reason they go up in 2s. So they go 1, 2, 4, 6, bang, you've now lost your marks. What's this one here? Well, this is a GCSE one, might ask you to convert this. Well, how many 1s do we have? None. How many 2s? None. How many 4s? None. How many 8s? 1. So it's 8, no 16s, no 32s, no 64s, but 1, 1, 2, 8. So it's 128 plus an 8. It's going to get you 136. Get yourself off to Edmodo. Go and try number systems binary to denary, giving you way longer you're going to need to do it, like 60 minutes, just in case you want to have a look at the slide deck, replay any of the video, that kind of idea. Have a go. As usual, if you suck at it, I can delete it and you can have another go. Will be added to your gradebook. So hopefully, in this part of the lesson, you understood how binary can be used to represent whole numbers. And really, this video and the video before, the introduction, would have, and the going through this in class and going through the test, would have taken you up to your first lesson. But we are going to carry on with other videos, which will be coming shortly.